work through how you'll do one of the problems from the simulation, and this is also very similar to how you'll set up your problem for your quiz today. So the calculation, the math that you would work out, the way the problem is presented to you is different, but the steps you'll take and the calculations you'll do will be exactly the same. I'm doing granite for this problem, so you want to find the specific heat of granite. And something that's different about my problem compared to yours is I'm going to start with a mass of 150 grams. So this is not exactly from your lab. I've changed up the initial mass, so my numbers will work out a little bit different, but the process will be exactly the same. So you can mirror this in what you're doing in your lab. All right, so what I like to do for this is I like to make a list of the MC and delta T information that I have for each substance in the problem. So I'm going to do my granite over here, and then over here I'm going to do my water. And for each one, I'm doing a heat transfer problem. So for each one, I'm going to need the variables M, C, TF, and TI. Right? And now I'll look in my simulation setup to see if I can find some of those numbers. All right, so my granite information is up at the top. So my initial temperature of my granite was 100 degrees Celsius and my mass was 150. All right. And then for my water in my initial setup, my water temperature was 25 degrees C. That's my initial temperature. And then my mass was the 2,500. All right, this is a heat transfer problem. The basic premise of this is that the heat will flow from one substance to the other. So in this simulation, we have a hot piece of granite going into colder water. So the heat will flow from the granite to the water until they come to the same final temperature. And that's the information you get from that graph. So that final temperature, the 25.85, is the final temperature of the water, and it is also the final temperature of the granite, because heat is going to stop flowing when we've reached thermal equilibrium. So this is 25.85. So in any problem where your heat is flowing from one to the other, so any calorimetry problem, you have one final temperature that you are measuring. All right. And then I need one more piece of information. So the specific heat of the metal is the thing I am trying to solve for overall in this entire problem. So that's not what I need. So I need to look at water. Now, water has a very well-known specific heat. It is 4.18 joules per gram degrees Celsius. All right, so that's always the specific heat of liquid water. We use that a lot, and in calorimetry, it's really convenient that we know that. And this information was given to you in the lab as well. So that piece is what you were given. All right, I have all my information for the water. So I'm going to solve for the heat, the Q of the water. So I'm going to plug all my numbers in on the water side. So Q equals my mass of water, which was 2,500 grams, times my specific heat of water, 4.18 joules per gram degree C, and then times my temperature change. So you always do your final minus your initial. So we will do 25.85 minus 25. So when you subtract these two, you'll get 0.85 degrees C, and then you'll multiply 2,500 times 4.18 times 0.85. So if you do that, you will get 8,882.5 joules. All right. And in this problem, or in this entire lab setup, the sig figs are not very well distributed in the simulation. Like for example, it's highly unlikely that the balance that they're using only goes to the tenths place. So for this problem, I am just going to record my specific heat to 2 digits after the decimal point, since that's what the specific heats are in the table that you're given. Um, there are actually rules when you multiply and divide and add and subtract for sig figs. And so just in this simulation, I'm just going to ignore them and just do the workout. Just kind of be aware of that, because the temperature should have like a decimal place at the end, so you know that it goes to the ones place. So don't worry about sig figs for this at all. The simulation doesn't have enough information for you to do that. All right, so now we found the amount of heat for our water. In a thermal equilibrium problem, so whenever you're doing these calorimetry problems, whatever heat you get for the water is the same amount of heat that you have for the metal. The sign just changes. So this amount of heat flowed from the metal to the water. And so our Q for our metal is exactly the same. We just change the sign. So now this is negative 8,882.5 joules. And now that we've got the heat figured out, we can now solve for the C, because we have all the variables that we need. So now I will set up my equation over here for my granite. So I have my Q equals the mass of the granite. And remember, this is the number that's different. My mass of granite was 150 grams. You guys all have 75 grams when you worked yours out. Then we're solving for the C, and then we have our TF. Now, our final temperature is that temperature they both came to. Oops, undo that. So that's my 25.85, and I'm subtracting from that the initial temperature of 100. So this temperature change comes out negative, which is what we want, because we do have a negative sign on the other side of our equation, and we need that to cancel out because specific heat is always positive. So the negative here and the negative on the here and the negative here are going to end up canceling each other out to leave us with a positive specific heat. All right, so mathematically, I'm going to do negative 8,882.5 joules is going to be divided by 150 grams, which is multiplied by negative 74.15 degrees C. And hopefully you can see here your units are joules per gram degree C, which is exactly what you want for a C. And this comes out to be 0.799, or if we're going to go just 2 digits after our decimal point, 0.80 joules per gram degree C, which is just 0.01 off from what granite's specific heat is in the chart that we have. All right, so this is the specific heat of granite. All right, so that's the steps you'll always take to do one of these. You find the information for each substance you have, fill it all in. You'll solve for the heat of one of your substances, change the sign on it. That will become the heat for the other substance, and then you can find the missing piece there.